By the end of this video, you should be able to apply the concept of stoichiometry to calculate the mass, moles, or concentration values from acid-base reactions. 2. Use the titration data to determine the concentration of an acid or base required for a neutralization reaction. Let us now learn to apply stoichiometric calculations for acid-base reactions. Let us say we have a hypothetical balanced chemical equation. 1A gives 2B. According to the balanced chemical equation, 1 mole of A reacts to form 2 moles of B. In the stoichiometry chapter, we discussed how to calculate the amount of product formed given the amount of reactants. That is, if we know the number of moles of A that we are starting with, we can determine the number of moles of B that can be formed using the stoichiometric coefficients as a conversion factor. Similarly, we can predict how many moles of A is required to produce a given amount of B using the same stoichiometric coefficients as conversion factor. Let us say instead of moles of A, the mass of A in grams is given. We can convert the mass of A into moles of A using the molar mass of A as the conversion factor. And then we convert the number of moles of A into number of moles of B using the stoichiometric coefficients as a conversion factor. And if we want the mass of B formed instead of moles, we can convert moles into mass by using the molar mass of B as the conversion factor. Now let us say the reaction is happening inside an aqueous solution. Instead of the number of moles of A, we are now given with the molarity of A and the volume of the solution. Using these two, we can calculate the number of moles of A. And once we know the number of moles of A, we can calculate the number of moles of B by using the stoichiometric coefficients as conversion factor. And once we know the number of moles of B, we can either calculate the molarity of B or volume of B given the value of the other. Let us now apply this to an example. It takes 100 ml of 0.25 molar sodium hydroxide solution to neutralize 250 ml of a HCl solution. What is the concentration of hydrochloric acid solution? The first thing we do to solve any stoichiometric problem is to write a balanced stoichiometric equation. 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide to form 1 mole of sodium chloride and 1 mole of water. In the problem, some information about sodium hydroxide is given and the information about hydrochloric acid is being asked. We can interconvert between the number of moles of sodium hydroxide and number of moles of hydrochloric acid using the stoichiometric coefficients as conversion factors. Let us now write down what is given. The molarity of sodium hydroxide is given and the volume of sodium hydroxide is given. The volume of hydrochloric acid is given and we need to calculate the molarity of hydrochloric acid. It is like solving a puzzle. We start with sodium hydroxide and move towards hydrochloric acid. First, we can use the molarity and volume of the sodium hydroxide to determine the number of moles of sodium hydroxide. Then, we can use the number of moles of sodium hydroxide and the stoichiometric coefficients to determine the number of moles of hydrochloric acid. And in the third step, we can use the number of moles of hydrochloric acid and volume of the hydrochloric acid to determine the molarity of hydrochloric acid. We first start with the volume of sodium hydroxide solution, that is 100 ml, and we multiply this with the molarity of sodium hydroxide to get the number of moles of sodium hydroxide. The molarity of sodium hydroxide, I am going to write it as 0.25 moles of sodium hydroxide per 1 liter of solution. And instead of 1 liter of solution, I will write 1000 milliliters of solution, so that I can cancel milliliter of solution and milliliter of solution in the numerator. And now my answer is in number of moles of sodium hydroxide. In the second step, I convert the number of moles of sodium hydroxide into number of moles of hydrochloric acid. For that, I need to multiply this with a conversion factor that has moles of sodium hydroxide in the denominator and moles of hydrochloric acid in the numerator. And from the stoichiometry coefficient, we know that for each mole of hydrochloric acid that is reacting, we need 1 mole of sodium hydroxide. Moles of sodium hydroxide gets cancelled. Now my answer is in moles of hydrochloric acid. Next, I am going to use the moles of hydrochloric acid and volume of the hydrochloric acid solution given to calculate the molarity. The volume of hydrochloric acid solution is 250 ml, which is 0.250 liters. If I divide the number of moles of hydrochloric acid with the volume of hydrochloric acid solution, I get 0.1 moles per liter or 0.1 molar hydrochloric acid solution, which is the final concentration of hydrochloric acid solution. In the problem, it is given that 100 milliliter of 0.25 molar sodium hydroxide solution is required to neutralize 250 milliliters of HCl. Now, how do we determine these numbers in the lab? We use an analytical technique called titrations to determine these values, and therefore the concentration of hydrochloric acid, which was not known before doing the experiment. We will discuss more about titrations in the next slide.
First, let us start with a basic question. Why do we do an acid-base titration? Titration is an analytical technique to determine the concentration of an unknown acid or base solution that is given to us. Next, how do we do the titration? Let's say we are given a hydrochloric acid solution with an unknown concentration, and we are supposed to do a titration experiment to determine its concentration. In order to do the titration, we need an aqueous solution of a base with a known concentration. For example, if we are in the lab, we can prepare a 0.100 molar sodium hydroxide solution. Generally, we take a known volume of solution with an unknown concentration in a conical flask. The solution with unknown concentration is called analyte. So, in this case, we have hydrochloric acid as an analyte, and we started with 20.00 milliliter of hydrochloric acid in the conical flask. Next, we take the solution with a known concentration in a burette. The solution with known concentration is called the titrant. In this example, the titrant is 0.100 molar sodium hydroxide solution. We add sodium hydroxide solution from the burette into the conical flask containing hydrochloric acid in small increments. Every time we add sodium hydroxide to the conical flask, sodium hydroxide reacts with hydrochloric acid present in the conical flask according to the following stoichiometric equation. That is, 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide to form 1 mole of water and 1 mole of sodium chloride. We keep adding sodium hydroxide to the hydrochloric acid solution until we reach a point where all the hydrochloric acid present in the conical flask is completely reacted with sodium hydroxide that is being added. The point where the amount of titrant, that is sodium hydroxide, added is enough to completely neutralize the analyte, hydrochloric acid solution, is called the equivalence point. After the equivalence point, the sodium hydroxide that is being added to the conical flask stays unreacted. Now, how do we determine when the equivalence point is reached? We cannot see the hydrochloric acid molecules in the conical flask. For now, let us say that there is a way to determine this point. Later on, we will discuss how do we determine this equivalence point. In this example, the equivalence point is reached after adding 21.6 milliliter of sodium hydroxide. Now we can use the information obtained in the experiment to determine the concentration of hydrochloric acid that we started with. We know that it took 21.6 milliliter of 0.100 molar sodium hydroxide solution to completely neutralize 20 milliliter of hydrochloric acid solution in the conical flask. The number of moles of sodium hydroxide required to neutralize the hydrochloric acid can be calculated by multiplying the molarity of sodium hydroxide with volume of sodium hydroxide. If we calculate that, we get the number of moles of sodium hydroxide is 2.16 millimoles. From the balanced stoichiometric equation, hydrochloric acid and sodium hydroxide react in a 1-to-1 ratio. Therefore, we can say that the conical flask had 2.16 millimoles of hydrochloric acid at the beginning of the reaction. We can now calculate its molarity using the number of moles and volume. It comes out to be 0.108 molar. We started the experiment with an unknown hydrochloric acid solution. We did the titration and determined its concentration to be 0.108 molar. This is precisely why we do a titration, to determine the concentration of an unknown acid or a base solution that is given to us.
The next big question is, how do we determine if the equivalence point is reached? There are two ways to do it. One, we add a special dye called as an indicator to the titration mixture. This indicator changes its color at or very near to the equivalence point of the titration. An example of an indicator used for acid-base titration is phenolphthalein. Phenolphthalein is colorless in acidic solution and pink color in the basic solution.
In the previous example, if we add a couple of drops of phenolphthalein to HCl solution before the beginning of the titration, the solution first appears colorless. After the equivalence point is reached, the solution is completely neutralized and the phenolphthalein still appears colorless. The next drop of sodium hydroxide added turns the reaction mixture basic, therefore triggers a color change in phenolphthalein from colorless to pink. This is the signal that we look for while doing a titration. We stop adding sodium hydroxide as soon as we see a persistent pink color in the reaction mixture. The point at which the indicator changes its color is called an endpoint. At this point, we have a slight excess of the base in the solution. Ideally, we would like the endpoint to be as close to the equivalence point as possible.
The second method to determine the equivalence point is by plotting a titration curve. We will discuss this in the next semester. Let us do an example problem. A 25 ml sample of sulfuric acid is titrated with 0.150 molar sodium hydroxide. The burette reads 15.3 ml at the end point. Find the molarity of sulfuric acid solution. First, we need to write the balanced stoichiometric equation. Let us translate the reaction into an equation. Sulfuric acid H2SO4 reacts with sodium hydroxide NaOH and it forms a salt which is sodium sulfate and water H2O. Next, we need to balance this reaction. We have two sodiums on the product side and only one sodium on the reactant side. So we multiply sodium hydroxide by 2. Now we have two oxygens on the reactant side and only one oxygen on the product side. So we multiply water by 2. Now the equation is balanced. So from the stoichiometric coefficients, we can say that 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. We can use these stoichiometric coefficients to interconvert between the number of moles of acid and number of moles of base. In other words, if one is given, we can find the other one out. Let us now write down what is given. We know that we started with 25.00 milliliters of sulfuric acid. And we need to determine the concentration of sulfuric acid. The concentration of sodium hydroxide is given as 0.150 molar. The burette reading at the end point is 15.3 milliliter. This is the volume of sodium hydroxide required to neutralize all the sulfuric acid. So, we use the concentration of sodium hydroxide and volume of sodium hydroxide to calculate the number of moles of sodium hydroxide. Once we know the number of moles of sodium hydroxide, we can calculate the number of moles of sulfuric acid using the stoichiometric coefficients. Next, we can use the number of moles of sulfuric acid and volume of sulfuric acid solution to calculate its molarity. We start with 15.3 milliliters of sodium hydroxide and convert milliliters of sodium hydroxide into liters of sodium hydroxide using a conversion factor. Milliliters of sodium hydroxide gets cancelled. Now we have liters of sodium hydroxide. We convert the liters of sodium hydroxide into moles of sodium hydroxide by multiplying it with molarity. The molarity of sodium hydroxide is given as 0.150 molar. We can also write this as 0.150 moles of sodium hydroxide per 1 liter. Liters get cancelled. Now we have moles of sodium hydroxide. Next, we need to calculate the moles of sulfuric acid from moles of sodium hydroxide. We will multiply this with a conversion factor that has moles of sodium hydroxide in the denominator and moles of sulfuric acid in the numerator. From the stoichiometric coefficients, we know that for each mole of sulfuric acid, we need 2 moles of sodium hydroxide. The moles of sodium hydroxide gets cancelled. Now we have moles of sulfuric acid. If we divide the moles of sulfuric acid with the volume of solution in liters, we get the molarity of sulfuric acid solution. The volume of sulfuric acid is given as 25.00 milliliters, which is 0.0250 liters. If we do the math, we get 0.0459 molar.